Greetings. So we are still dealing with paging problem, and we will today learn about the so-called marking algorithms. Oops. Marking algorithms. Now these kind of algorithms can be deterministic or non-deterministic ones. These are just this is just a template for a whole class of algorithms. So an algorithm if it's of course online, an algorithm for the paging problem when do we call this as a marking? As a marking one. Marking one if it's operating as follows. So first, in the cache, each page can be either marked or unmarked. Each page can either be marked that's why they are called marking algorithms. Oops, marked, I mean. So marked or unmarked. You can think this marking or unmarking as having a Boolean flag. So, and then if a cache miss occurs and the cache is full, so we have to discard something, then first, if all the pages are marked, then we unmark all the pages. Then we unmark them, all the pages. Second, independently from this, we have to discard an unmarked page. Now, the algorithm doesn't specify which one to discard amongst the unmarked ones. We discard an unmarked page. And third, if we serve a request, then the page is in the cache, of course, after serving, and then we have to mark that page. Accessed, we mark it. Well, I should say here not if but when. So whenever a page is accessed, then we have to mark it. Period. Let's see an example. Let's see an example. So as usual, the cache size is just 3, and the number of inputs is, say, 6, the number of pages in the disk. And for example, sigma can be something like, say, 1, 2, 3. This is just to fill the cache. And then say 5, 3, 5 again, 2, say 3, 1, 4, just to use the 4 as well, say 2, say 3, 1, 3, 5, 4, why not? Oops. So in this case, a marking algorithm can work as follows. So initially the cache is empty, and then of course we put the 1 into the cache. But then we have to mark this one, because this is accessed. So the star will indicate a mark, and no star is indicating unmarked pages in the example. And then of course we have to include the 2 and mark it, and then of course we have to include 1, 2, 3, and 3 also became marked at this point. And now 5, we just have to process the 5, and now since it is a marking algorithm, if we have a cache miss and all the pages are marked in the cache and the cache is full, then first we have to drop all the marks. So we are here 1, 2, 3, and then we have to discard an unmarked page, say the first one, so we can always do discarding the smallest page, which means we are 2, 3, 5, but the 5 is marked because it was just requested. The others are not marked. And now what happens if 3 is requested? Then I will continue here. This is not a cache miss, but 3 is requested, so it's marked at this point. So although it's free, but it's now marked. And then if we just request for 5, we have to mark the 5 as well, but it's already marked, so it's not a problem. I'm just zooming in. Okay, and then 2 is requested, and 2 is also in the cache, so it's not a cache miss, but we have to mark this guy 2 star, 3 star, and 5 star. And then again 3 is requested, but this guy is in the cache as well, so 2 star, 3 star, and 5 star. We don't erase the marks at this point because it's not a cache miss. But then 1 is requested, so we first have to drop all the marks, and then we have to discard some of these guys, one of these guys. So if we just discarding always the lowest possible guy, then this is just the 2, which means I will have a 1 marked because this is the requested guy now, 3 and 5. And then a request for 4 comes, which means I will discard something because it's a cache miss, and at this point this guy is the lowest possible unmarked guy. So I will just end up here with the configuration 1 star, 4 star, 5. And then for handling the 2, I will just discard this 5. This is the only option here because that's the unmarked page. Oops, no, doesn't matter. I would like to preserve an ascending order on sets, but it's not a problem. Okay, then I'll have 1, 2, and 4 unmarked because 3 induces cache miss, and then I'm just discarding the 1 because that's the lowest guy, and I'll mark this 3 here. Then if I see this correctly, it's a 1 which is not in the cache, so it's a cache miss. I'm discarding the 2, and I will have 1 star, 3 star, and 4. And then 3 comes, it's fine because, well, it's in the cache already, good. But then for processing the 5, I will discard the 4, so it's 1 star, 3 star, and 5 star because this is excessive, and then I just got the 4, which will first erase all those marks, 1, 3, 5, and then it's 3, 4 star, and 5 because I'm just discarding the 1 there. Good. So that's what happens for this example run of a marking algorithms. Of course, I could choose the largest one. I could choose them, well, some of these guys at random. It doesn't really matter. So all of these versions will be marking algorithms. Now, why are we dealing with marking algorithms? Because there is a statement, a theorem, if you wish, which says that any marking algorithm is k-competitive. Now that's a statement, because for the deterministic ones, it means that the deterministic marking algorithm is optimal among the deterministic ones. Any marking algorithm is k-competitive. It can be better than k, but they are all k-competitive. Now, to prove this theorem, we will analyze again the phases of the input. Again. And now a phase ends when I'm unmarking the pages. Ends upon the unmarking step. I will show this on the example, that's why it's so long. On the unmarking step. So this means that, what do we have now? I'm just zooming out slightly. And I will again indicate the phase borders by blue vertical lines. So here, when the request for the 5 came, then that was the point when I just dropped the markings. So this is a phase boundary. And then I removed the marks when when I think here, when the 2, 3, 5 was the state, was the cache content, and then I get this 1, which means that this guy here is a phase boundary. And then the next step was, I think it was when we just got the 3, yeah, here. I'm just dropping just before processing the 3. And then I dropped the marks just before processing the 4, so that was the phase boundary. So this is how phases are computed, and if you just check this, here 1, 2, 3, we have k elements, k different elements. In a phase. 1, 2, and 3. Here also we have k different elements in the phase, right? So it's 5, 3, and 2, and that's all. Here we also have k different elements in the phase, 1, 2, and 4. Here we also have k different elements in the phase, 1, 3, and 5. And here, of course, this is the last phase, so it might happen that there are no more less. So here I have exactly k different elements, here I have exactly k different elements, here I have exactly k different elements, and so on. Now that's important, and the first one is because this guy, so what happens is the following. On the phase line, here, everything is unmarked. That's why it's a phase border, unmarked. And then a number of requests arrive, and for each new request, for each distinct request, I introduce a star. Here I will mark the 1. Here I will mark the 4. Here I will mark the 2. Right? Here I'm marking the 5. Yeah, that was at this point. I was marking the 3. It was this point. 5 was already marked, so it doesn't count as a new mark. But here 2 is also marked, and 3 was already marked, so it's not marking. So in each phase, which is not the last one, exactly k marks are distributed. So in a phase, we give, well, either k marks or even less than k. So in the last phase we are, well, in this case we just marked 1 element. So we mark, so we mark at most k elements. In the last phase it can be less than k, in all the other phases it's exactly k. At most k elements. And if we have a cache miss, then we definitely mark something, because that will be a new element which is just moved into cache, and we mark it. So this means that there are at most k cache misses can happen during a phase. According to a marking algorithm. Yeah, at most k cache misses. We will also show that for any algorithm there is at least 1 cache misses during a phase, right? And also we will show that there are at least 1 cache misses are needed in each phase. Now these two statements, so this is not for the longest forward distance for any algorithm, including the optimal one. So for any action sequence, I guess. Of course, these two statements will prove me the k competitiveness, because it says that in each phase the optimum is at least 1 and the algorithm will produce at most k, so the algorithm divided by the optimum is at most k. So it will prove k competitiveness, but we still have to show this. In each phase we need to spend at least 1 amount of something. Now let's just analyze this, and I'm not exactly marking the phase boundaries, but I'm just shifting them by 1 to the right. So I will just mark this place, and I will just mark this place, and I will just mark this place, and I will just mark this place. Now I say that what happens at this point? No matter what your algorithm is, at this point, no matter what your algorithm is, this guy is in the cache at this point. So here the 5 is in the cache, right? Here at this point 1 is in the cache, because any varied response means that you have to move the page into the cache if it's not there, or if it's there then you don't have to do anything, but you won't discard this. So at this point the first element of the original blue phase is always in the cache after handling it. So here 3 will be in the cache, and here 4 will be in the cache. Now why is this important? Because here we have a phase, and a phase contains exactly k distinct elements, which means that here in the remaining part I have at least k minus 1 distinct elements, which are not the first one. K new elements. So here it's non-5 elements. Why? Because during this whole blue phase there were k elements, k distinct elements. 5 was one of them, so the remaining k minus 1 should occur here. In this case, for example, is the 3 and the 2. Okay, so these are k minus 1 different elements. And also here, that's why I shifted, this guy here is a new element, because it starts a new phase, which means that I just gave out the stars, so everything is starred, and this guy starts a new phase because it's not a member of these. That's why we have to drop all the marks, and this guy makes cache miss, which means that this guy here is also new. So I have this element, and after this point here in this section there are exactly k new elements. So k, say non-5 elements. If 5 is this guy, elements. Now since 5 is in the cache at this point, there are only k minus 1 places remaining in the cache, and here we have k different elements, which means that at least one of them is not in the cache. That guy will definitely make cache miss. So for example here, no matter what my cache content is, here it can be say 2, 3, 5, whatever, not necessarily a marking algorithm according to a marking algorithm, but 5 is definitely in the cache, after handling this 5. And if I have 2, 3, and 5, then okay, 2 and 3 will not induce a cache miss, but this one will. At this point, I can have 1, 2, and 5 in the cache, but in that case, this 3 will cause a cache miss, and so on. So I have exactly one element, which is definitely in the cache, k minus 1 other elements, but k elements are arriving, so one of them will definitely, at least one of them will definitely create a cache miss. And then after that, there is this section again here. Again, here there are k different elements, 4, 2, and 3, k different elements, and 1 is another element. This guy is in the cache, definitely, at this point. And I have 3 other elements which cannot be in the cache along with this one, because that would need a cache of size of k plus 1. So I don't have enough space. At least one of these guys will cause a cache miss. Now, for example, here, if I had this 1, 3, and 5, it means that 3 won't cause a cache miss, but both 4 and 2 will cause a cache miss. But even in the best possible case, say I could have 1, 2, and 4 on the cache at this point, because 2 is a member of the previous phase. But even then, 3 will cause cache miss. And again, on this part, 1, 5, and 4 are 3 new elements. 3 was one element, and next, and along with the 3, there can be k minus 1, so that's 2 in this case, different elements in the cache, but here we would need 3 of them. So in each phase, there will be someone, or in each right shifted phase, in each right phase, there will be exactly at least one element which causes a cache miss. So that's how it's proved that one cache miss is always needed in each phase, and a marking algorithm will only make at most k cache misses, which means that the ratio is at most k for these two quantities, which means that the marking algorithm is exactly k competitive, because it cannot be better than k competitive according to our previous theorem. And for last part, I will just make a note here as just a note, or just a small remark, and the LRU, which is the least recently used algorithm, is a marking algorithm. It doesn't explicitly use the marks, it's a marking algorithm. It doesn't explicitly uses the marks, but it is a marking algorithm because, well, take the input sigma and create those phases as before. Those phases as before. Which means that phase ends just before the k plus 1th different element. Just before the k plus 1th distinct element. And then we can say that a marked element is one having a timestamp from the current phase from the current phase the unmarked means that it's from the previous phase. And it works. So for example, we are just doing this on a short example. So if I get 1, 2, say again 2, why not 3, say 4, say 1, say 5, say 4, and then I say 1 and I'm 6 and 1 and 2, why not? Then how the least recently used algorithm works. First, it just starts with an empty cache. I'm just zooming in. Then in the first step I will just include this one there. Then in the second step 1 has still the timestamp of 1, 2 will get the timestamp of 2, and then I get the 2 again, which means that I just update its timestamp. It's now in the third step, and then I just include 1, 2 in the first step, 2 in the third step, and 3 in the fourth step. Then 4 arrives, it's a cache miss, and I'm just updating the one with the smallest timestamp, which means that I will get 2, 3 at 4, and 4 at 5. Then I have this 1. I've just discarded that guy, but never mind. So I'm dropping this guy here because that's the least recently used. Cool. Then a new element again, but that's at this time this guy is the one with the smallest timestamp, so it's just 5 at 7. Then now that's good, I'm just updating the timestamp, so it's 1 at 6, 4 at 8, and 5 at 7. That's also good, I'm just updating the timestamp. It's 1 at 9, 4 at 8, and 5 at 7. And then a 6 comes, and I will just discard the guy with the smallest timestamp. So it's 1 over 9, 4 with 8, and 6 at 10. Then I don't have to discard this guy because it's in the cache, but I'm just updating its timestamp. 4 at 8 and 6 at 10. Is it finished? Yep. So, and then I have to discard this guy because that's the smallest timestamp in the cache. So it's 6 at 10. Yeah, great. So this is how the least recently used algorithm runs on this particular input. And if you just check what happens if you mark those phases exactly the same way as before. So here we have 1, 2, 3 different elements, and here comes the fourth one. So I'm just marking this here, and then 4 is the first, second, third, but this was already seen in this phase, but this guy is new, so this will be the fourth, which makes this line the phase boundary. And then 6, 1, 2, this is a single phase again, so there are only 3 phases in this particular input. And then if we just check what happens, okay, so in the first part we are just loading the cache, that's right, and the statement was that if something gets discarded, then its timestamp is from the previous step. So I'm just at this point, of course I discarded the 1 with timestamp of 1. At this point, this is timestamp 4. 1, 2, 3, 4. This was timestamp 5. So at this point, these two guys have a timestamp from the previous phase. And indeed, here 1 is a new element, and I discarded this guy having a timestamp with the from the previous phase, and here I had a new timestamp. So right now only so I already marked in a sense the element 4 and the element 1 because they are two guys having a timestamp from this phase. This guy has an old timestamp. Old timestamp means that it's from the previous phase. So I will discard this, and right now 6, 7 and 5, so 6, 5 and 7 are each at least as large as 5, which was the starting timestamp of this phase. So this means that they are all marked, but we don't have to discard them when the request for 4 comes, because that's in the cache and 1 is in the cache, but then the 6 arrives, and then we just erase all the marks and start a new phase. 5, 6, 7, 8, 9 at time point 10. And we just update the cache, and then right now this guy here is marked because it has a timestamp from this phase, from this phase, the current phase, but these guys are, well, sort of unmarked because their timestamps are old, are from the previous phase. So we will, when the 1 arrives, I'm just updating its timestamp to 11, but right now this counts as a marked occurrence in the cache, so these two guys are marked. And then when the 2 arrives, I'll discard the 4 because it has an old timestamp. But right now, each of these guys have a new timestamp, a current timestamp from this current phase, which means that they are all marked, and then at the next point there will come a new phase, which is fine. So this is how the least recently used algorithm is marking. We just have to, well, discard some of the information, and instead of keeping track the exact timestamp, we just say that if my timestamp is from the current stage, from the current phase, then I'm marked. And if my timestamp is from the previous phase, then I'm unmarked, then it's fine, and it will make the least recently used algorithm to be a marking algorithm, which means that it is k-competitive, because all marking algorithms are k-competitive. So LRU is k-comp. The least recently used algorithm spends at most k times more than it's needed. By the way, the algorithm FIFO is also k-competitive, but we won't prove this. It's not that important. It's also k-competitive, but FIFO is not exactly a marking algorithm. So it's k competitive for different reasons. But what we've learned in this particular video is that what a marking algorithm is, and right now we know what it is, and the marking algorithms are good, at least among the deterministic ones, because the marking algorithms all of them have an optimal competitive ratio, so they spend at most k times more money than they should. So that's for today. In the next part we will apply some sort of randomization to the mix. Till then, bye bye.